Hello everybody and welcome back to the parallel programming and computer architecture class. And in this unit we will be studying parallel communication patterns. We will start revisiting what we have learned so far about CUDA and CUDA architecture and programming on the software side of things and the CUDA programming model. And then we will break down different algorithms and different approaches to solve problems that require processing a large amount of data, and break them down into specific patterns of communication between processes. And from that point on, we will try to draw out certain features that you could look at when you're analyzing a program that you're or a problem that you're trying to program, and then extract out these patterns. And then when you do that, then you'll basically be able to fit a parallel communication pattern onto it and program it. Before we go into the details about how we can, what kind of different patterns of communication are there that we can exploit trying to address a problem or trying to program an algorithm to solve a specific problem that requires, again, a large amount of data, we'll need to look at what we have actually in terms of hardware and software, and what these combinations of our hardware and software do, and then see how we can format our problems into the the manners, the ways that our hardware and software architecture process. So to do that, let's take a look at our heterogeneous programming model that CUDA gives us. And as you remember from our discussions so far, the CUDA programming model is really interesting in that it allows you to work on a familiar programming architecture, a familiar programming model that essentially is very well known, and a lot of us have a good deal of experience with, and that is essentially host programming, utilizing a compiler such as the C++ compiler. Now, the way that CUDA programming fits into this model is that it's through the so-called heterogeneous programming model. And that is, we will basically work with two different compilers. The host compiler, or the CPU compiler, that takes our program and compiles it with the architecture and the instruction sets of our host, or our CPU. And then alternatively, we have the CUDA compiler, or the device compiler, that takes pieces of code that we want run on our device or on our GPU, graphics processing unit, and compiles it with the hardware architecture of our CUDA device, our GPU device. And the way that these two devices work with each other is through communicating with each other through global memory. Basically, the parts of the data that we want the GPU run, what we're going to do is that we're going to post them and put them on global memory. GPU will take them and process them on its global memory, and then the results will be accessible to the CPU through the PCI Express bus. And we have discussed that in the hardware level, and we've seen how it actually lays out and is implemented in the software level so far. So we have two hardware entities. We have the host entity, or the CPU entity, with its own copy of memory and its own functionality, which is basically going to be the main functionality of our program, and also setting up of our GPU or our device code to be able to send out and be implemented on the GPU. And the GPU will have, or the device will have, its own memory, its own GDDR5 and own shared data and own register banks that are shared within simple processors within each streaming multiprocessor, and the memory that is accessible to all of streaming multiprocessors. And also, the functionality, the code functionality of our GPU device is going to be implemented through kernels. Kernels are essentially functions that we have our host send out to the device, and then the device will run these functionalities, these functions on the data that is copied into the memory. And again, the memory accesses are designed and implemented through the PCI Express and the communication with the global memory. So the way that this works actually is that anything that we have on the host memory is not accessible to the device, and anything that we have on the device memory is not accessible to the host. The means of accessing these data, or sending these data back and forth between our device and our host, is through the implementation of our functionalities of copying between host to device or device to host, essentially the mem copies that you've seen so far that that occur on through your global memory. Now, the functionalities that are going to be sent to the kernel or to the GPU are going to be tagged with the keyword global. And any function with the keyword global is essentially a function that will be outsourced and will be given to the device to run. So a typical processing cycle in a CUDA program works like this. You have your CPU or host to allocate all the storage and data units that are required. That will occur both on the CPU and the GPU. To allocate memory on the CPU, you create pointers, and then you either use or rather alloc or malloc functions, C functions, or the new function, which is basically a C++ function, to allocate memory on the CPU memory or on the host memory. You will also have to have your host, your CPU, allocate storage on the GPU, and that happens through the CUDA malloc function that you basically define a device pointer, and then you allocate a certain size for your data on the GPU. The next step is when your CPU, after allocating memory on the device, copies data from CPU to GPU. Now I apologize for my little typo here. So the CPU, basically after using CUDA malloc to allocate memory on your device, is going to use CUDA memcopy to copy the data from the allocations on the host onto the memory of your graphics processing unit or your graphics card. Once that happens, your CPU launches the kernels that you also create. Again, you create kernels basically with the __ global __ and then void or int or double or whatever, and then your kernel name. And if you needed to have data pass, so these are going to be your parameters that again are going to be essentially the data on your GPU. So these are going to be the data pointers on GPU, and then you launch. So basically your CPU launches the kernels. The way that it works is basically you utilize your kernel name with the triple chevrons of the sizes you want, with the data you pass, data pointers basically, and that way you launch your kernels. Once the launch occurs, the kernels will be sent out to the GPU, and GPU basically runs those kernels. And we'll see how it happens on the GPU, and what kinds of things you can rely on happening, and what kinds of things that are not guaranteed by your GPU. And being aware of these is going to be very, very important for us as well. Once the kernels execute and finish up their processing, then the CPU, or the CPU part of your code, will have to be responsible for copying back the results from your GPU onto your CPU so you can work with them. And this transfer again happens through a CUDA memcopy in the reverse direction of what happens on step number 2. So when you copy in step number 2 your data from your host to device, you use CUDA memcopy, and the parameter that you pass to it are going to be the data pointers on the host and the data pointer on the device. And then you use the keyword CUDA memcopy device to host, or rather host to device. So that's going to be the thing that happens on step number 2. And on step number 4, you basically use the reverse keyword, CUDA memcopy device to host, transfers back the data from your GPU memory back onto your CPU memory. So what is the big idea in defining your GPU computation, and how you should be able to run this program? And what is essentially the big picture? What is happening in your program? How should your GPU computation program be modeled after? And this is basically the idea. So this is basically the idea. We essentially try to find a thread of execution that takes care of the building block processing that we need to do. And we take this as a serial program. So basically, depending on how your program works, you'll have to come up with a shell. And here it essentially translates into a kernel that takes care of the very basic bare-bone process that you need to do. Then you wrap this shell into a kernel. Wrap it in a functionality that then you can replicate over and over and over again, or rather have your GPU replicate it over and over again, and then run it on the device. Once this kernel actually is implemented and the functionality is designed for it, then we'll tag it with a keyword that associates it with the code that needs to be compiled with your CUDA compiler and be sent to your GPU to run. If this kernel were to run on your CPU, then it would run once. Basically, if this was just a simple function that would take some data and do some process on it, it'll only happen once, because you have like one CPU that is taking care of operating the serialized code. The way that it associates with the device or with your GPU means that after you specify as the programmer the parallelization of this functionality, then your GPU will take it and take care of the parallelization, or rather the replication of this process over your GPU. And so once you invoke the kernel to run on your GPU, the GPU will run many copies of this kernel as needed as separate threads. And the good thing about this paradigm is that the programmer can set the number of threads to run on the GPU, essentially defining the parallelization of that is needed to run on the GPU, and also the patterns of parallelization, or rather the relationship between these parallelized processes that are running on the GPU. The programmer can specify that. And later on we'll see what CUDA paradigm, what CUDA architecture does allow you a little bit more in details, and what it does not allow the programmer to do. And basically, for the efficiency's sake, of running things efficiently on the GPU, it'll take care of. So we'll see these in a little bit more detail later. So now that we have this big idea, let's see what is it that your GPU is good at, and what is it that your GPU does. One of the most important things, one of the most major things that your GPU is good at is that it is good at efficiently launching a lot of threads. If you look at any other kind of parallel paradigm that is out there, you may be looking at having a very limited number of parallelizable hardware at your disposal. For example, 4, 6, 8, 16 CPU cores that you can parallelize your programs with. And then when you do that, then essentially as a part of your parallelization on the CPU side, especially given that you have good size computational architectures at your disposal, is your parallelization would happen on more of a software level, in that you rely on hyperthreading or multi-threading and things of that nature, and time sharing, time slicing between the threads that are given. In CUDA, we rely heavily on launching a very large number of threads, each of which will perform very simplistic and mostly basic processes, if you will. And if you're able to create an architecture, to create a programming model that goes after this, you'll be able to optimize your code tremendously and efficiently. And we'll see this in a little bit, how it can be done and what kind of patterns are best exploited with this parallel model. So what does it mean to run lots of parallels, lots of threads in parallel, and how CUDA is good at doing this? Is having these threads run in parallel makes, or essentially takes away, a good deal of serialized computation in the form of loops that otherwise you would have to run. And if you think about it, before each iteration of loop executes, the previous iteration would have to be completed. And that is what makes the step complexity of some processing applications on the serialized patterns and serialized format inefficient, especially when you have a lot of step complexities. There's a lot of steps that need to be run to complete the task. Whereas if you parallelize those steps, then, especially if your application does have certain step independence, certain iteration independence, you'll be able to have all these steps run at the same time, or many of these steps run at the same time. And this will increase your throughput efficiency of your application. And as we saw previously in Unit 5, when we talked about throughput versus latency, we noticed that we talked about if you're using a bus to transport people between 2 points, between two destinations, then you'd better fill the bus, because it's going to be slower than going with a personal car. And the way that you get efficiency out of going with a public transportation system such as a bus is if you transport, while your bus is working, transport many people with it, as opposed to having a half full, a tenth full bus going between places. So CUDA and running lots of threads in parallel essentially gives us this capability. This gives us this tremendous amount of parallel units that have the capability of running at the same time. And the way that we will optimize the efficiency, the way that we will the efficiency that we get out of this processing unit is if we basically have all of these threads, all of these computational architecture hardware at our disposal to be occupied and to be running threads at the same time. So the key here is to run your threads in parallel. You don't want to have your threads to have to wait for each other to finish a task. And later on we'll see what kind of patterns are best exploited, and what kind of patterns, if you fit your algorithm in, will enable your threads to basically run in parallel to give you efficiency in terms of completing many tasks in a certain amount of time in a given time. So your threads, it's rare to have threads to basically take one data, operate on it, and be done with it. Although there's a lot of applications, there's a lot of problems that fit in this model of threads completely being independent of each other and just working on something, finishing it up, and be done with it. But the majority of the tasks that we would have to do requires our threads to be able to communicate with each other, our threads to be able to work together to run and to solve the problem efficiently. And so when it comes to the point that we will have this platform, we will have this functionality, then it would behoove us to basically try to study how our threads may communicate with each other, and in what certain circumstances and conditions thread will not be able to communicate with each other. So what does that all mean? Threads essentially are the building block, are the soul of our parallel computation here. And what is key here is thread communication. What does this mean in terms of data? It means that if you have a part of memory, your threads may need to read from the same unit, or they may need to write in the same unit, or they may need to swap or exchange information. So if all these arrows here are threads that are run on your GPU in parallel, the first case scenario is when all of these threads need to have access to the same memory unit and to be able to read from it. Now, as you see here, the only bottleneck here is that only one thread at a time can read from a unit electronically. But the good news is that this bottleneck is going to be tremendously small compared to the execution time of a thread. So the simplest case, when threads require to read the same unit of memory, it can be done really, really quickly. And on top of it, it does not really change much the computation that is going to happen within these units. So basically, that's probably the simplest case of communication that we will see. The second case is when you need when your threads may require to write into the same unit of memory. There are two problems here that we need to be aware of. The first problem is the same as reading from the same unit of memory, is that when a thread is trying to write into a memory unit, the contention is actually very, very small compared to the lifetime and execution of the thread itself. It would be able to happen over a couple of clock cycles. So that's not really going to be a big issue for us. The biggest issue, though, is that we need to make sure that the integrity of our data is preserved when we have multiple threads writing into the same unit of memory, because, as we see later on, we won't know which thread will have the first access and which thread will be the last to access the memory. So if you needed to have the integrity reserved of your data unit, you need to be a little bit more careful and think about your process, especially in this case that contention may happen, especially in this case that collision may happen. So for example, if your ideal case of these threads running into the memory was if the ideal was thread number 1 would be the first, the third thread to be the third one, and the fourth thread to be the fourth one to write into this memory. If that were your ideal case, there is no guarantee that these threads will do that. So there may be the case that thread number 4 is the first one to write, and thread number 1 is the last one to write. So they basically overwrite the functionality of your application. And the third application, the third process is going to be also a combination. Essentially, threads may read data, and then at some point in time, they may require to exchange their data and information with each other, swap their information with each other. So if this were the case, then you would have to be extra careful about what is going on and how this data swap and data exchange is going to need to take place to preserve your computation. Because again, the fact of the matter is that once you have your thread written, and as you notice from our previous examples and previous programs we did so far in the class, you can specify what your thread does, and then you specify how many of these threads and in what kind of combination you want run. But that is beyond that is completely beyond your control. Your GPU will take these threads, will allocate them on the hardware, and will run them. And there are certain limitations to this process in that you will have no control over what's going on beyond this step. So you need to be able to programmatically implement those needs. Now, to help us understand and break down these computations and to help us be able to write programs that are basically run efficiently and utilize the efficiency and the flexibility of our GPU model, in that it'll take the threads from us and then allocate them itself and run them. To be able to do that, we would have to start looking at specifying certain kinds of communications that are happening that are general, and then if we can draw out specific models of patterns of communication between threads, then we can basically look at our problem that we're given and then try to fit it in one of these models. And then if we know how to program each of these specific models, then we'll be able to easily program our problems. So it's basically a two-step problem. You're given a problem, you look at what kind of patterns of communications you are aware of and that you can program and that your CUDA can efficiently run. Then make your problem fit into one of these models, or maybe a combination of the models, and then program them. Doing so also helps us study how we can basically make our programs run more efficiently, because there are certain kinds of things that are going to go on the GPU when memory accesses happen. And if we can look at those and see which one of these patterns are most fit for a certain kind of memory access, then we can basically optimize our programs even further. Now, without further ado, let me just talk about 4 very basic and important parallel communications or patterns of communications that we need to be aware of, and that we can program efficiently and easily on the GPUs. There are the 4 that we'll talk about in this unit are going to be map, gather, scatter, and stencil. Now, they go from simple to more and more complex, and we'll see how we can fit them and what each mean. Map is the simplest form of communication. Is when you have tasks that require to read and write to a specific memory unit. Now that means that each thread will be in charge of one unit of operation and will just work with that unit of operation. So the tasks are sort of independent, so your threads really don't need to communicate with each other. The second communication pattern is a gather, and as the name suggests, tasks would read multiple locations from memory and then write into a specific unit. And we'll see how it actually is implemented. A lot of filtering will happen in this manner. Scatter is the opposite. When you have a task, read one element and then split the content of that element and write into multiple units of memory, multiple elements of memory. And as you can see, scatter is going to be a little bit more complicated and probably a little bit more difficult to implement, because that is when there's the possibility of multiple threads requiring to write into the same unit of memory. And finally, we have stencils, when the tasks don't just read multiple units in memory, but rather the multiple units that they're reading from the memory fit into a specific fixed pattern of neighborhood in the memory. And if we know how those patterns are and how we can implement those patterns, we'll be able to extract a lot of good efficiency from our model. So let's delve into each of these models and operations and study them a little bit further. So first, let's take a look at map. As I said, map is the most simple. We've done this program so far a couple of times, so it should be the most familiar to us. In a map operation, we want a set of items to process, and we know how to process each one of these items independently. A good example of that is basically the simple CUDA template program that is set up when you use in Visual Studio the CUDA 5.5 runtime template. The idea is you have an array. Actually, you have two arrays, array A and array B, and all you need to do is to add these arrays element by element. So to implement this, we know that the sum of the elements of the arrays is going to be element by element. So as long as we can write an operation that takes one element from array A and add it to the corresponding element in array B and storing it into array C, we will be good. So this fits very easily into the map operation. We have a set of items to process. We know how to process one item. Map takes care of this for us. We specify essentially the operation on each element. Basically, it's like take one element in, generate the output for that element, and then perform the operations independently of each other. And as we have seen, CUDA is really wonderful in this model, because all we need to do is to write one kernel. So essentially, you need to basically write one kernel, map it to your thread index, and then invoke. Invoke that kernel. And then your operation is going to efficiently run. Next order of our business is going to be the scatter operation. Let's see, or the gather operation. Let's see how gather does this work. In the gather operation, we want a set of items to process. Also, we know how to generate the output that is calculated based on a number of items within the set of items that we need to process. Gather is the operations we do on these elements. We take a set of elements as an input, generate one output, pair a number of input elements, and then we store them. So if you notice that in map basically is a simplified gather, in that we basically take one of the elements of the input and generate one element per that input element in our output. In gather, instead of taking just one input, we take a bunch of the input elements from our input data. So if this was your input data, in the gather operation, you gather values from a set of elements in your input, in this case every 3, and then you store the result of your process into one of these elements. Now this is very easy because basically essentially not that it's more complicated than your map operation, but it's the next level. It's the next step. The only contention here is that when, for example, when the thread that's in charge of this element is basically trying to access the other 2 neighboring elements, then the contention is going to be happening right on these two units, but the result is going to be written in one element. So gather is essentially a many-to-one map operation, whereas map is one-to-one mapping operation. Scatter is the opposite of gather. If we want to have if we want a set of items to process, and then we know how to generate, pair input element, multiple output elements. Scatter is the operation that we do on each of these items. Take your input element, essentially as in data, and then take each element of the input data and then perform an operation on it and then spread it out into more than one output element. Also, if you notice here, map is a specialized scatter operation in which you basically scatter each input element into one output element. Whereas in scatter, you scatter one input element into multiple output elements. And as you notice here, the problem is going to be the contention of writing when, for example, the element that's processing this unit, the thread that's processing the 1 over, is going to have to write into these 3 units. So these 2 memory units are going to be the contention problematic areas when you write. Now, there are certain means, there are certain ways of operating and writing these programs that require scatter operations using atomics, basically locking each output unit when a thread needs access, having it done the operation, and releasing the unit for the next thread to operate is one means of solving or resolving these contentions. And also another means is essentially to reformat, rethink your problem. And the majority of scatter operations, you can write them in the form of a gather operation. And we'll see how that can be done in a little while. And finally, is the stencil operation. Stencil operation is basically when you have a set of elements, a set of items to process as input, and you know how to generate values per neighborhood of inputs. So it's a specialized kind of gather operation, and that is if the gather pattern, if the neighborhood of the data patterns that each thread is gathering fits in a pattern, and we call that pattern a stencil operation. For example, the gather operation that I showed you before gathers the elements from a 3 neighborhood. So for each element I, you gather the value, the contents of I, contents of I minus 1, and contents of I plus 1. So if you look at this thread and say name this thread number J, then you gather from J minus 1, J and J plus 1, and then you may actually gather elements with like different ways. Like for example, take element I and use it directly, take element I minus 1 and I plus 1, and then multiply them by a weight factor, and then perform this operation. This is the so-called stencil pattern. So your stencil in this case is going to be a 3-dimensional, or rather a 1-dimensional 3-element pattern of data, and say you multiply this by 0, multiply these elements by 0.15 or something like that. And so and that is how your scatter operation, or your gather operation works. And then you write the result into one element, the associate element to the thread, and that's basically your stencil. So you take a neighborhood of elements in and generate your output per neighborhood in your input elements, and that is essentially your stencil. There are certain examples of stencils that we can utilize. There are von Neumann patterns and Moore patterns of neighborhoods. For example, in a 2-dimensional neighborhood, von Neumann basically takes the element in the center and then one element on top and bottom and elements to the left and right. This we also call 4-neighbor pattern. In a Moore pattern, in a 2-dimensional Moore pattern, you basically take all of the 8 neighboring elements on a diagonal and vertical and horizontal, and as well as the input. So it's basically an 8-neighbor pattern. And so these are used a lot in signal processing, for example, filtering your data with an 8-neighbor or a 4-neighbor von Neumann or Moore pattern. As you see here, for example, in a 4-neighbor pattern or 4-neighbor stencil, for each input you require to have access to 4 other neighbors. In an 8-neighbor, for each input element, you require to have access to its 8 neighboring elements, or rather 8 immediate neighborhood. There are also 3-dimensional patterns for von Neumann patterns and for Moore patterns. For the von Neumann pattern, for example, for a 4-neighborhood pattern, you've got your input data, and then in 3 dimension you get access to 4 units alongside of it. And then for the Moore patterns, for each data point, you'll basically need to get access to a 3-dimensional block of elements, basically just like that. So if you were to have access to the central data in the middle of this block, then you would have to get all of the neighborhood elements in 3D to access. Now, why are we treating these as a special gather operation? We call them stencil operation. The idea here is the data reuse. Basically, for each element that we are using, there's a lot of overlap, and that needs to be happening. And since our graphics processing unit, our CUDA hardware, when we request 1 unit of data, it basically gives us a neighborhood of data. If we are aware of data reuse patterns that we have here, we will be able to optimize our operation. So instead of having multiple accesses to the same memory unit, if we can specify these patterns and fit our data into these models of data reuse, we'll be able to have 1 memory access and perform a bunch of operations at the same time. So what does that mean? Let's take a look at, for example, this 2D von Neumann pattern. When we are actually accessing the central unit here, the center element here, as a part of our process, we need to have access to these 4 neighboring elements, right? Now, what if our next thread over is going to process this guy? So as a part of that, it needs to access the 4 neighboring elements, which means that this element that we are processing here, say element ij, is processed twice, once as a part of itself being processed and once as a part of its rightmost neighbor being processed, as well as its leftmost neighbor being processed. So when we're processing these two, to process those, we would have to have 3 times access to element ij, right? So if we can have these patterns and reuse the element ij when we accessed it, then with just 1 access to the memory, we'll be able to use it for 3 neighboring threads. And so this data reuse is a pattern that's going to be helpful when we are performing these calculations. And finally, as I said, there are additional patterns of operation that we have that are that don't fit directly into map, gather, scatter, or stencil. One of the most basic examples of these patterns of operation, which happens over and over frequently, is the operation that is called transpose. A transpose operation will take an element in some order and reorder them, or generates another ordering of these elements. And that element is called a transpose. For example, it's actually a mathematical operation that happens on matrices. So let's say that we have a matrix A, and this matrix is in row order, meaning you've got the rows A, B, C, D, E, and F. And then you want this operation, so basically this is a 2 by 3 matrix, and you want this to be in the form of a column order matrix. So we call that transformation as a transpose, and we denote that as A transpose, which means that we'll take the first row and we'll make it into the first column. So it's going to be A, B, C, and then you take the second row and make it the second column, D, E, and F. So this now becomes a 3x2 matrix. And the operation that we perform here is called a transpose operation. This happens frequently and occurs a lot in our processes, and this process is called a transpose again. And you can see this in terms of basically array of elements versus elements of arrays. What does that mean? For example, let's say that in C++ we define a struct, for example A, and then in the structure we have an int small a, int small b, and then int small c, right? And then if we create like 10 of them, and we call it like A ELE 10, this will create basically an ELE 1.a.b.c, and then ELE 2.a.b.c, and so forth. As opposed to if you create a structure B, which will have like 10 A's and then 10 B's and 10 C's, right? So in this second case, when you define just one B, then you'll have 10 elements in it. So the first item that we have here, we can basically think of this as being created with the first structure. So basically you create, for example, element 0, which is going to have its own A, B, and C, and then element 1, right? And this is going to be having its own A, B, and C, and so forth. The transpose operation basically makes it into elements of arrays. So this is going to be now your B structure, which is going to have one element A and B and C, and then it's going to have a bunch of these. And there may be a need to perform these operations interchangeably, and that operation that you perform here to go from the element of arrays to arrays of elements, so this is going to be an array of elements, and this is going to be element with arrays inside of it. This operation is going to be a transformation called transposed. It can be done in different ways. You can format it into a gather operation. So for example, if you want to perform this transpose, if you've got your elements created, so this is going to be your ELE 0 for its A, B, and C, right? And then element 1 for its A, B, and C, and they're placed in memory. If you wanted to perform a transpose on them, you could do them as a gather operation. So that will create all A's here, gather all B's here, gather all C's here. And so as a result of this, a gather operation. Or you can create it as a scatter operation. Basically, you take your elements and then you scatter them around. So a transpose operation can be considered in these formats. So if you create one thread that gathers, so this is going to be one thread that gathers the data from your input, or if you create one thread of operation that scatters the data in the output. And which one of these are going to be more efficient? How are you going to program this transpose operation is going to be important in determining the complexity of your operations, and specifically the data in the input and the problem that you're trying to solve. So which one of these patterns should we use? Should we use a map operation, gather operation, scatter operation, stencils, or transpose? It highly depends on the applications we have. It highly depends on the efficiency that we want to get and the amount of processing that needs to be performed. And of course, a lot to do with data reuse and the model of processing that we have. Are there any other communication patterns that we need to be aware of? Yes, there are, and we will see them later, and we will see how they operate and what they are, and in what kind of circumstances we will use them. So let's take a look at an example, and let's see what kind of communication patterns occur in this example. So our example is that we have an output array and an input array, and then we have a two-dimensional block of threads. So each thread will have a thread index x and a thread index y, and what we want to do is essentially multiply each of the input elements by pi, or take the input element from our two-dimensional array and reformat it into the output element. So that's line number 2. Or we basically multiply element I minus 1 if I is not divisible by 2. So if the thread index I, or the x, is not divisible by 2, multiply it and store it in I minus 1 or store it in I minus 2. And if it is divisible by 2, so if the thread index is an even index, we basically take the input element and the one before and the one after it, and then we calculate the average of these input elements, and then we multiply them by the number pi, or 3.1415, and we store it in the output element. So which one of the operations are these? Are they map, gather, scatter, stencil, or transpose? So I let you guys think about it for a little bit, and then we'll get to answer these one at a time. All right, now let's answer our questions one at a time. So what do we have here? We've got an input array and an output array. And then we have a two-dimensional pattern of threads. And each thread will have a thread index I and a thread index j. All right. So I is thread index.x, and j is thread index.y, or rather, thread index.x and thread index.y are going to be our j and I. So when we basically take the input at element I to be the thread index.x, and we write it into the element I of an array. So if you have a thread index x, it's going to take this input and write it into the output. This is going to be a map operation. Basically, each thread index x, is going to write into the output thread index y. So it's going to be a map operation, but our operation is going to be strided. We're not going to write anything into these elements in our first operation. So we just take the x thread index x and write the element into the thread index output x, just multiply it by 3. Now, if you look at the second operation, what we're going to do is to take the inputs in the second operation. What we're going to do is to calculate an index from the input, and then take that output element and put it in one. Take the input element and put it in one output element. So we've got a 1-to-1 mapping. But the way that it works, and I'm going to tell you that this is going to be a transpose. And I'll show you how this transpose happens. So let's take a look at the input element here. And our thread patterns. Of x being, let's say, the rows thread index.x, and y's being thread index.y. Now, the block dimension is how many rows and columns we have, and let's say that we have a 2 by 3, or let's make it simplified, a 3 by 3 block of threads. So our block dimension here is going to be 3. So what I'm going to do is I'm going to create an index here. That's going to be my thread index dot y, right? So that's my j, and then take my thread index dot x and multiply it by my block dimension, and then create a number here. So what is that number? So let's say that I start with number thread index 0, 0. The index here is going to be element 0. Okay. How about 0, 1? Thread index 0 times block dim plus 1, thread index y. So that's going to be my index 2. So index 0, index 1, index 2. And also, so this is going to be block number 0, 2. Now, since I have block dimension 3 here, the element 1 comma 0 is going to be element number 3. Element 1 comma 1 is going to be element number 4. And 1 comma 2 is going to be element number 5. Okay, so that's my input side of things. How about the output side of things? Okay, what is my output side of things look like? It's going to look like thread index y times block dimension plus thread index x, right? So this index is going to be thread index dot x plus, say in my case, 3 times thread index dot y. Let's see how that's going to look like. So for element 0, 0, this is going to be 0, and this is going to be 0 times 3, so it's going to be 0, right? How about when I have element 0 comma 1? So my 0 comma 0 goes to 0. How about my 0 comma 1? Right? Thread index x is going to be 0, and thread index y is going to be 1. So that's going to be multiplied by 3. So my element 0 comma 1 is going to be my element 3 here, right? My element 0 comma 2 is going to be element 6 here, right? So as you see, my input element number 0 is going to be written into output element number 0, but input element number 1 is going to be going to output element number 3, and input element number 2 is going to be going into output element number 6. So as you notice here, I'm basically taking my row order matrix like that, and then I scatter it into a column order like that. And that is exactly the transpose operation that we talked about earlier. So the operation here that takes a two-dimensional input and reorders it into a one-dimensional input and reorders it into a one-dimensional output, it's going to be a transpose operation. Now let's go to the next items and see the next 3 items. What operations are they? So I'm going to erase what I have so far. Okay, so let's now take a look at this next 2 operations. Let's see what this is going to do. Actually, I'm going to basically think of these 2 things at the same time as one operation. So if you look at this element, it's actually guarded by an if statement. So this in this operation, only odd number threads are going to execute. Let's see how they look like. So this is my input array, and this is going to be my output array here. And so I have a number of input elements and the same number of output elements corresponding to the input elements. And as I said, this only executes odd threads. So thread number 1, thread number 3, and thread number 5 are going to execute. So this is not going to be a map operation because it's not a 1-to-1 mapping. It's not going to be also a transpose operation because transpose also needs to be 1-to-1 mapping. It takes your element from, for example, as we saw earlier, from a J major order and make it into an I major order, right? So it's not going to be a transpose operation either. It's not going to be also a stencil operation because we will not have, for every output element, we will not have an input element, or vice versa. Now let's see what happens with this operation. So if you look at thread number I, each thread I is going to generate 2 outputs, one for I minus 1 and one for I plus 1. So basically it's writing into multiple output elements, and it's going to basically get the input value and scatter it in the output value. So it's going to take output element and redistribute the input elements into it. So thread number I is going to increment the contents of output element 0 and output element 2. Thread number 3 is going to increment the output element 2 and the output element 4. Thread number 5 is going to scatter into output elements 4, and if there were an output element 6, it's going to scatter into output element 6. So these is going to be cumulatively a scatter operation. Okay, now I'm going to change color here. For the last one, I'm going to essentially use the same data, and now in this case, the else operation is going to run on my my odd elements, right? So when I is my even elements, when I is divisible by 2. So for example, it's going to only run for elements number 0, elements number 2, and elements number 4, and so forth. So thread number 2, for example, is going to add the content of location I to half of location I minus 1 and I plus 1. So it's going to gather values from these other 2 elements and calculate some sort of average for them, and then multiply by 3 and then store into element number 2. Same, element number 4 is going to gather from number 3, number 4, and number 5, and then store into number 4. Element number 0 is going to somehow attempt to read from 1 before itself and 1 after and store into number 0. So this element is this process. So this process is going to be a gather operation, or you can think of this also as a stencil operation. So the kind of communication patterns we've seen so far, you've got 1-to-1 mapping, which is basically your map operation or your transpose operation. Both of them are 1-to-1 mappings. We have many-to-1 mappings in the form of gather operation, when you gather operation from many elements from your input array and create one element for the output. We have many or one-to-many operation, which is basically your scatter operation, and that is when you gather, when you take one of the input elements and spread it into multiple output elements, many output elements. And a specialized case for gather, which is called stencil, that basically you have a neighborhood of several elements in the input elements that you want to gather data from for one particular output element. Some other operations and communication patterns we haven't talked so far are in the form of all-to-one. It's called reduce. We'll see that later on. And all-to-all patterns of communication. There are 2 of them, very, very important: sort and scan. And we will see these 2 patterns of operations in our future units. And we will see these elements, how they occur, and how you can program them with your CUDA patterns.